Hi, everyone. This is Colton Randall, and I'm here to present my research paper on the evolutionary mechanisms for antibiotic resistance and some new drugs and research that's out there for them. Off with, most Americans don't really believe that bacteria actually evolve, but in fact, there was a study that was produced by CGTL 2016 that said, how many times do news articles report the word evolve when talking about bacterial antibiotic resistance? And they actually found that only 1/5 of American media articles describe bacteria as evolving. But in fact, we do know that bacteria do evolve. And I like this image because it shows that bacteria are similar to humans. They're similar to any animal species. They're under the rules of Darwin's natural selection and survival of the fittest and descent with modification. And bacteria acquire antibiotic resistance through these mechanisms and through these rules of evolution. There's a couple definitions I wanted to just briefly touch on. First is an antibiotic. An antibiotic is something that is able to kill or inhibit the growth of another bacteria so as to increase the fitness of the bacteria that can produce it. Bacteria that are resistant are obviously able to resist this, are able to destroy the antibiotic, and are able to get rid of it or stop it from inhibiting its growth. And so they have an increased fitness from that as well. It is interesting to note that not all bacteria are completely resistant. Some are susceptible to antibiotics or completely resistant or not resistant at all. And some produce antibiotics and some resist it. There's a big question, is antibiotics and resistance and the evolution of them naturally occurring in the environment, or did the human use of antibiotics increase it? And the real answer to that is it naturally occurs. And there are significant studies that can trace the lineages of bacteria-resistant genes back to thousands, if not millions of years. And so antibiotic resistance has always occurred. And that's probably because of the Red Queen hypothesis, which we've talked about, how the bacteria really have to compete. They have to be continually evolving. If one bacteria is able to produce an antibiotic and the other is not able to resist it or is unable to produce another one back, that bacteria will be killed. And so it's survival of the fittest, and if they're unable to evolve, their species will go extinct. And I thought it was pretty interesting, though, to note that when Mycobacterium tuberculosis was first treated with streptomycin, they saw a really big increase in the resistant strains. And so the actual answer is humans don't cause antibiotic resistance, but humans' use of antibiotics may increase natural selection and increase the rate of antibiotic-resistant bacteria developing. And so that's an interesting note on how humans are involved. Natural selection is the biggest thing here. Natural selection occurs in the bacterial population. You have to, like with all species, there's variation in the population. Some bacteria that can resist antibiotics. The antibiotics are used, kills all the bacteria that are unable to resist the antibiotic, but the one that it is able to resist survives and is able to reproduce through mitosis and also through horizontal gene transfer, which we'll talk about later, to create a big colony, which is what we call dissemination. And then you get a completely resistant strain in the end. So the first way that variability occurs for natural selection to act on these bacteria is through random mutation. It increases the variation in the population by doing something that helps the bacteria survive antibiotics, whether that's a bigger membrane, it helps it pump antibiotics out, prevents the binding of antibiotics. Mutation causes this, and this is a good way of showing that when a mutation occurs, it allows it to survive, and as that process occurred through natural selection previously, that bacteria continues to survive and thrive, while those who don't have that variation die. There is an interesting part where mutation is influenced by humans, and bacteria have a really short generation time, so they can reproduce from just these one little resistance to thousands of little resistant bacteria. But they're also a haploid, which means that chromosome, so any mutation will be expressed because there isn't a second chromosome to mask that mutation. So mutations are a really big deal for variation in bacteria. And there's a study with some cystic fibrosis patients And what basically this study showed was these patients are really susceptible to continual pneumonia infections, and so they get pneumonia a ton. And what they found was doctors prescribe an antibiotic to stop the pneumonia, but not all of the time the bacteria is killed. The patient doesn't use it correctly, or the doctor doesn't prescribe a correct amount. And what can happen is the bacteria are able to they're able to produce mutation rates at a higher rate, because those that are susceptible move on because they weren't completely killed by the threshold, either by the patient or the doctor, and they can accumulate mutations. And so it can actually increase the rate of mutation and the amount of mutations that a bacterial population has until they're completely resistant. Horizontal gene transfer is another big area for bacteria, because they're able to actually exchange their genes through plasmids and transposable elements. I really wanted to highlight plasmid exchange because bacteria are able to, through this diagram, exchange the genes that could encode for antibiotic resistance. So they can give it to another bacteria in the population, which really increases the amount of bacteria that have the antibiotic resistant genes. There's an interesting study with E. coli and the PB15 tetracycline, and in this study they increased they wanted to see if there's a correlation to the amount of resistance in the population compared to how much they're exchanging their plasmids. And as you can see from this graph, this was the original bacteria populations. These are bacteria populations that have had mutations accumulated on them. But you can see from the original graph, R is for resistant, I is for intermediate, and S is for susceptible. And as you increase the rate of horizontal gene transfer, you see a staunch increase in the resistance. And so plasmid exchange really does increase resistance in the bacterial population because it gives it more variation for natural selection to act upon. Are another big area of antibiotic resistance and evolution of them. Superbugs really are just what happens when evolution occurs over a long period of time, when natural selection continually selects upon the bacteria that are the fittest, that have the best genes. And as mutations accumulate and as plasmids and transposable elements are exchanged, you can really see that superbugs start to develop. And these are really scary because no antibiotics are able to be used on them because they have all the genes necessary to survive those antibiotics in their environment. And there's a lot of different hypotheses about how superbugs occurred. One is that natural selection really causes it, because over time they'll accumulate and the best bacteria will continue to survive. Another is that there is a single common ancestor that all specific superbug strains came from, which is possible, but the leading theory right now is that natural selection causes these superbugs, and they're capable of killing thousands because we don't have antibiotics to fight them. But all is not lost, and this is really the last area that I wanted to touch upon, because some really interesting research going into how we can actually stop these superbugs, and there are evolutionary mechanisms that they're using to do this. One of the biggest ideas right now is to just find new antibiotics to stop them, but the evolutionary mechanism that I like is called drug switching. And basically the idea with drug switching is that the bacteria that are developed a resistance to antibiotic A, we'll say, what you do is you allow them to develop a resistance to a specific drug, and then you switch it on them so that they are not resistant to this other antibiotic. Well, over time, obviously, random mutations will allow it to be resistant to antibiotic B. And so over time, if you continue to lose antibiotic B, the bacteria will develop resistance to B and hopefully lose their resistance to A. And you can switch back to B, which allows you to use antibiotic B. Once they are completely resistant to B, you switch back to A. It's really a new theory that's developing, and it's really essential that we understand the bacterial genome. But on a natural selection level, it really makes sense because you're able to select for the best in the population and then switch it on them, and then select for the best in the population and switch it on them. If we're able to know the genes that bacteria are using for that, could be a really successful treatment. Also, we have bacteriophages. Bacteriophages use as well. It almost seems counterintuitive because bacteriophages carry transposable elements and plasmids, so they could carry antibiotic-resistant genes. But it's pretty interesting because there are genes like the CRISPR-Cas gene, which have developed a resistance to bacteriophages. And the reason is because some bacteriophages, like lytic bacteriophages, will actually end up destroying the bacteria, so it reduces their fitness if they're infected by them. So the bacteria develop, through mutations and through natural selection, a way to block bacteriophages and the plasmid exchange and transposable elements. That is, they develop these new genes like CRISPR-Cas that when the plasmid or the transposable element is introduced into the environment, they kick it out. And so then they have a higher fitness because they can kick those lytic phages from taking over their system and killing them. And so you use natural selection in the same way to develop bacteria that say, hey, we're not going to take these horizontal gene transfers, which can reduce the amount of resistance in the population. So it's really interesting that these are some of the ways that they will continue to develop and understand as we go forward. Differences and a few of the studies that I cited, and I'm grateful for all of you for being in the class this semester, and it was a great semester. So see you guys later.